Yeah, so we're gonna be talking about how to train your neural network. Aadi and Drew, we already sort of went through how a neural network works, like pass in the data, get some prediction, and we also did a bit of calculating how bad the model is doing. So we have an idea of loss, the error, cost, whatever you want to call it. So those are the things, but now is the real part. How do we train the model? How do we make it learn the idea? So it's not really practical. You don't need to know this. A lot of the things are done for you if you have the idea what you want to do. But it's great to know anyway. But it's on a very academic side, very theoretical. But it leads to other practical side on the other hand. If you want to train a model, you want to create actual model that can work on real data. It requires different sets of skills, but I think it's still important. It wouldn't take much time anyway. So I think the best way to start is, did I take a look at something? A simple neural network, like what we did last time. You have your input, X, right? Feed in to a node with the weight value. Draw that high. And it take a bias. This will give you a prediction. Right?
Speak up louder.
Yes. Hear that? Yeah. So yeah, they have the meeting. I don't want to. But anyway, input parameters. You multiply, you add that, you get a prediction. Right? Now, the idea of a neural network is that we try to reduce something called loss. So the loss is, we have a lot of way calculating it, so I'm just going to call it this fancy L. But usually, you take in another value, which is the target. Supervised learning. Like what should be the correct answer. And this target and the input are coming from the data set. You don't usually know the target in the real world, and this is the only part that you do in the real world. So this is the model. Right? And this is the loss part that gives you the loss. So that's what we have. We already sort of go through a lot of those many times. We didn't actually do a lot of real practical stuff. It's just simple, a single number in, single number out regression. Aadi did classification ideas back last week, not yesterday. But yeah, so that's about it. Now, what we want to do now is reducing loss by changing parameter. And the idea is that you change it so that the loss is low enough, not just for this input and target, but for any input it's never seen before. We want it to be able to generalize any input it take it. So it doesn't memorize that this picture is a cat. You can see a different kind of cat and it still understands that that is a cat. So that's what we want to do. And I'm just going to write something down. So we want to reduce loss by changing the parameters. So this is parameter, single specific parameter. It's either weights or bias or any one of those. The new one is equal to the old one, the current one. We add something. That's what we want to do, right? We want to update the parameter by something. We don't know what, we don't know how, but this is how we want to do it. Update it, get the new one, and use it so that it can predict better prediction later on. There's a lot of ways of doing this, but the most common one and very unconventional right now is that what if I take one of these parameters, W, let's say, and I increase it by a small amount, super small, and we will talk why it needs to be small later. I increase this, I keep everything else the same, put it back, and I recalculate the whole thing again. That means after I increase, I recalculate it. It will give me a new loss, right? Because if you change something, that means the loss will be different.
You sure that you will scratch your neural?
Yes.
That's good.
So this new loss, there's two things that we can observe from here. And it's very important that you have to get this now. New loss is either, and I want you to answer this question. What does it mean if the new loss is larger than the current one? And what does it mean if the new loss is less than the current one? These are the current loss. Right? You change something, you recalculate the whole thing, you got the new loss, and there's two options. What does it mean if it is larger? What does it mean if it is smaller? Any?
Larger means you're going further away from your target, and smaller is even closer.
Okay. Yeah, that's the idea. If your new loss is larger, that means increasing this will increase the loss, and you don't want that to happen, right? So if it is larger, that means we want to reduce our weight, that weight over there, not anything else, but that weight. And if it is decreasing, what does it mean? It means that increasing this will reduce the loss. And that's what we want. That means we have to keep increasing it. Right? Simple. So, yeah, that's the whole thing. We literally just can do that. Just go through all your parameters, increase it, do the whole thing, update your parameters. But it doesn't seem right. It seems like sort of just do random increasing. How much should we increase? Which it doesn't make any sense. But yeah, so let's get back to this real quick. Question mark over here. There's two important questions that we have to answer before we continue that. Those questions are number one. Which direction? If I want to change this parameter, which direction should I change it? Should I increase it or decrease it? And we already sort of answered that question by having this weird process, by increasing this and then deal with that later. That's what we have. The second question is, how much? We know the direction. We don't want to just increase it or decrease it, but we want to know how much exactly should we do it. And before we continue, can you see like way down? Everything's fine. Before we continue answering the second question, or even the first question, if you haven't answered it correctly enough, it's still a very weird process. So let's rewrite this whole thing a bit better. So what we're going to do is we're going to create this weird symbol delta. L is equal to new loss minus the current loss. Nothing. I just minus that and put it into a variable. But this variable is now can be used so that if it is positive, if it is larger than 0, positive, that means this new is larger than the old one. And we want to decrease our parameter. So the direction in which we update our parameter is negative. So whatever value is that we subtracted from our current parameter. And if the delta L is less than 0, this thing is smaller than that, we want to increase. So the direction is positive. Okay? But there is something interesting here, for those who haven't noticed. If L is larger than 0, essentially means that it is positive. That thing is negative. If it is negative, that thing is positive. And it's very important because the direction in which your parameter goes is just the opposite of this, whatever this delta L is. And we already know that the delta L is this thing. So the direction, I'm just going to write it here. If it's negative, but you delta up.
Just to clarify, we're considering a situation where the power loss will be from 0 to
Could be anything. You don't have to worry. I didn't even write the loss function. It could be mean square error, could be log loss, it could be anything you want, and the value could be anything. We just know the process of doing so. How do we figure out the direction?
I'm just wondering if your new loss and your loss, both will be right.
Sorry?
If your new loss and loss, both will be negative.
Usually,
negative result as well.
yeah, I see what you mean. Usually, loss function does not produce negative value. Loss function always produces something.
Maybe they're from 0 to 1 and put that sectical solution.
Sure, let's say it's 0 to 1. But yeah, usually loss can be from 0 to anything.
And in this case,
Actually, to your point, even if both of them are negative,
It's still
one of them can be larger or smaller than the other, resulting in the same value. -5, -3
Yeah.
is either a negative value, but if you do -3, -5, that's
but what if you have -5?
That means it is.
-5, -3.
yeah.
That means
still
it is
less-
That means the
decreasing.
downside is negative, which means you.
Yeah.
So the math
will
still
work.
works.
The math will
The-
work.
the math does
yeah.
work.
Trust
the
the
value
math.
doesn't matter as much as the
Yeah.
sum.
Yeah, just trust in the math. I shouldn't say that, but yeah, it will work no matter what. So I hope that you get the idea. This whole process over here. We haven't got far yet, but at least we got something. Whatever the delta loss is, the direction in which your parameter should go is the opposite. We still don't know how much, but it should be the opposite no matter what. That's the takeaway from it. Now, the next part is to figure out how much. And I don't have an intuition for this, but what we can say is, what if I just say delta L, which essentially means the change in loss, how much my loss has changed, either increase or decrease, divided by my change in parameter. Okay, so this in terms of math is usually mean average change, or you can say it is your change in loss with respect to your change in parameter. Okay, and the reason we do this and don't just use this is because different parameters change the loss differently. So by doing this, we know that it gives you the right amount of change. It's like if I change my parameter by this much, my loss changed by that much. What if I go the opposite way of using that value to change my parameter? Good idea? Yeah.
So for like the delta loss over delta change, so it's just taking the derivative, right?
You get to that. You get to that. Yeah. That's the idea. So change in loss divided by change in parameter, and since parameter is just a small value, it's just going to be that's how much we're going to use. So we know the direction, we know how much, we sort of just agree on this. There is no proof yet. I don't think I have a proof for this, to be honest, but we're just going to use it. Okay? So I'm going to rewrite our expression of changing stuff here back again. Your new parameter is now, I got to write it somewhere else, isn't it? Current one plus the direction and the value, how much. And since the direction is here already, I'm just going to divide it. So we got both direction and the quantity at the same time. And negative multiplied with plus is just negative. So we get this simple expression. Your current one, subtract this from your current parameter, you get the u. But it's not that simple. We multiply it with another number called the learning rate. And if you remember from 2 weeks ago, we have a value that Andrew wrote in the code. We multiplied with this value before changing his parameter. And the reason we do this is, as I mentioned from the beginning, is that we don't want to change the parameter just for this loss specifically, but for any other point in the data set, and hopefully any other point that's not in the data set too. But also, since we only change one parameter at a time, we want to use a small part of it. We don't want this alone to contribute to the whole change. We want everybody to help with the change so that our parameter can change a bit at a time. And then at the end, hopefully we get a good model that can give you good prediction. Right? So that's what we have. We still have this question of how do we calculate this? You can have that process, you could just go through those. It doesn't seem right. As a mathematician, not me, but mathematician, they don't like that. So they would do something, anything, to get rid of all of this process, to express it in one thing that you can use over and over again. They would do anything rather than actually work on some useful stuff, but it's cool. One thing that before we continue, is I just want to express something. Your loss, if you think about it, is just a function of all of your instruments. Parameter and target. It's a big function. Even though we have like mean square error that takes in prediction and the target, but you think of it, prediction itself is your model. So if you break it down, it's just a big function of everything. And since we're only concerned about the parameter, your loss is a function of your parameter. You change your parameter, your loss will change. So now I could express this idea in some elegant way, and that elegant way is simply delta L. I can write delta L now that I increase my parameter a bit. So I'm going to plus some value to it, h equals cy minus the normal one. So this unit loss. Okay. So h is a small number. So it's not just an arrow anymore. It is now something. And increasing it, recalculating the loss mean basically increasing the parameter. Put it back to the function. You got your new loss. Subtract it from the current loss. Same thing. And we don't have to pass this if statement anymore. We already have this and this. So we basically remove this if statement into an invasive sign. That means changing loss over changing parameter is simply the same expression over here. Divided by the change in parameter, and since we change the parameter by this value, it's just going to be there. Okay. Now that's something we can use even further. H is a super small number, and the reason we use small number is because we're not guaranteed that changing this parameter by a big number is going to reduce the loss regardless or whatever. We just want to notch it a bit and see how the loss will change. If we notch it too much, the whole thing might break down, and it's not a guarantee, right? That's why h must be a small number. And in math, we use something called limit to tell that. Limit of h approaching 0, meaning that h is super small, but not 0. but it still has the problem of how small. Like if you put 0.00001, the computer might have problem at calculating that. They are very bad at calculating small numbers, and you still don't know which number to use. You could just plug in a small number, and this whole thing will give you something. And that's actually worked back in the day. They call it a numerical method. You just plug in a number, you get something, but there's a lot of problems with that. So, for those who already know, this is a derivative. The definition of derivative, what it means, if you have a function of x, the derivative of f of x with respect to x mean that you change the x by a small number, divided, subtracted by the old one, and divided by that small number, and it gives you how much the f will change based on x. Derivative of x with respect to x. Derivative of f of x with respect to x. So what we have here is the same thing, but I'm just going to write using this weird symbol of your loss with respect to that parameter. Your loss function, again, is a big function that takes in a lot of input. And derivative only takes with respect to one input at a time. And since there are many of them, and with respect to only one, you call it a partial derivative. You will see this a lot if you actually get into it. But if not, it's just a derivative, right? This thing is this thing. And the reason we use derivative instead of using this expression is that we don't have to deal with small number anymore. Without changing anything, if you know the loss function, you can calculate it's the thing over there that we can update our parameter. Okay? Any questions so far? Yeah, it's quiet. Anyway, with that, we can rewrite our expression again. Your new parameter is equal to your current one.
So which part do you want to talk about?
Minus the learning rate.
Okay, I have to do getting a while, and then I have one more stage. So let's do it. See, the time goes, but you don't do it.
And this thing is essentially gradient descent, another term that you don't have to worry about. It's not gradient descent, I have to say. Don't worry about it. Anyway, yeah. It's not gradient descent. Gradient descent is, since there are many parameters, and this thing is only one at a time, you will have to take a derivative of the same loss function with respect to every parameter possible. And that gives you a list of that value. A bunch of actual. And this thing is the gradient of your loss function. So gradient simply means derivative of the same loss with respect to every single possible parameter. But we don't have to worry about that. This is a lot of noise, but hopefully that's fine. Any question, comment, concern? Yes. So we have an idea of calculating of how we update the parameter, and to do that, we need the derivative of your loss function with respect to that parameter you're updating. And we still, for those who already know the derivative, that's fine. But for those who don't, I'm not going to teach you. You can search it up online, Khan Academy, whatever you want. There's a lot of resource on that. So we're going to do a quick example from 2 weeks ago on Celsius to Fahrenheit. But this time, we're not just going to throw in an equation and then use some intuition or anything. We're going to use math and derive it back to the same equation that Andrew did last time and see if we got the same one. So last time we have, what was it? A simple Celsius to Fahrenheit. So I'm going to rewrite this. But this time we stop using the diagram. We're just going to use the equation that we usually use. This input going to multiply with weight plus bias, right? And we don't use activation function last time, but what if we do? This thing go into an activation function. Anything, the sigmoid, whatever you want, but usually you have to think based on your problem. Give you the prediction. That means, let's say we use mean square error to find the loss. Your prediction minus the target square. And this will give you your loss. Right? There's two ways of approaching calculating your derivative here. And that's two way is important if you're getting further into the nitty-gritty of finding derivative of a neural network in general. The first way, again, your loss is a big function. So what if I just write that big function, right? So number one, that big function is x multiplied with w plus b inside an activation function that could be anything. Subtract my target and square. That's my function, my loss function to be precise. And we want to change both weight and bias. That means we need partial derivative with respect to weight and with respect to bias separately. So the first thing is partial derivative of loss with respect to weight. And I'm not going to explain derivative, so I'm just going to do this. It's equal to 2. It follows some rule. I'm going to do the same thing for bias. If you remember from last week, we have this expression, but we don't have 2. We use loss and multiply with x. We don't have an activation function. This thing is just 1 for both of them. But if you have an activation function, this is how you do it. Put the derivative form of that activation function in the middle, and you will get and multiply it with the input. The intuition we have last time is that since weight is being multiplied with the input, changing weight requires something about the input. We want to know because it's influenced by the input. That's why we put back the input term here so that we get this. Not same for the bias because bias is enough. Right? So that's the first way. Big function, take the derivative, you got this. And this is something called symbolic differentiation. You have this, and you have to write down by hand. There are algorithms that can deal with that for you, but there's something inefficient. Is that for each of this, you have to rewrite the same expression over and over again. Although in the program, you could reuse this expression. It's the same thing, except the last one. But regardless, you need to know all of this to rewrite them again and again. So a smarter way, a better way, is what if I don't think of my function as a big function, but as a composition of function? What that means is that it is a function that takes in another function, that takes in another function. That's why I write it like this. X, this thing taking that thing taking that thing taking that. So composition of function is inside another. So if you have this sort of composition, you have to follow something called chain rule, where taking the derivative of this, but with respect to something all the way in here. And derivative rule has what's happening? In derivative, we simply can just use that limit expression to calculate any derivative of any function we want, but we don't do that anymore. what we do is we look for simple rule for smaller functions. For example, x to the n. And if we know the derivative of this, we can use this to compose bigger functions. Another function would be multiplication. So we don't have to know the derivative of this big function. What we have to know is the derivative of smaller function in there that compose this big function. And if we do know them, we can just multiply the derivative of each of those back. So I'm going to demonstrate that right now. I'm going to take the derivative of the last with respect to all the way in there. So first, let's take the derivative of this.
Something like that is
With respect to what? We don't take the derivative with respect to parameter yet, because this thing doesn't have parameter at all. But rather, it's taking something from there. So we're going to take it with respect to this, because we know this thing coming from here. We put it there. Now we can use that to multiply backwards. So derivative of your activation function is the derivative of your activation function, because you don't know what activation function it is. But if you do, just plug it in and everything will work. And I keep going back. Derivative of what was it? Y. From here we have two options. We have to
okay.
see what we're doing. We have this chain, and then when we go backward along the way, we have an option of branching out and take the derivative with respect to the parameter we want along the way. That means I could even take the derivative with respect to my input, which doesn't make sense in this context. But let's say you have multiple layers. That means there's more parameter all the way to the end. You can use this to keep going down and keep branching out. As opposed to symbolic differentiation, this is called automatic differentiation. And in the neural network term, it's what we call back propagation. Back propagation. And usually, a lot of this derivative, I'm just going to rewrite this. We just have this symbol, but now let's actually do the derivative. So the derivative of this with respect to this is just 2 multiplied with that. Multiply 1. And if I go backward, I multiply with the derivative of an activation function. And if I go backward again, I have 3 options, which is with respect to my weight, with respect to my weight, that means I get x. With respect to my phi, this is just 1. With respect to my input, is my weight. Derivative of this with respect to weight. This term has weight, this term doesn't have anything. It's 0. X is just a constant, that's why you have x here. Weights alone become 1. It's a power rule again. You can think of this as the w to the power of 1. Derivative of this is the this is the formula. I'm just going to write it down. Something to the power of x, something of n. You do this, multiply, subtract the power away. This thing will give you just 1. That's why 1 multiplied with x is just x. So I have this sort of graph from that side to this side. And if I want to find the derivative with respect to w, I already have those values, and I can just multiply with x, and I will get this. So I can use it, update it, right? This term we already calculated from the forward pass. So this thing alone can break down, even further. That means you don't have to recalculate this again. You already calculated while we're doing it forward. You have this, plug it in here, multiply with 2 and 1, and then keep going backward. The activation function, we're going to pick something like sigmoid for now. And something interesting about sigmoid is that its derivative is somewhere to write. Even though the function is complicated, and if you actually do its derivative, it's also very complicated. But you can express that in the same term of the activation function itself. So,
and this is the dot. The dot from this change if it's fine. I have it down
the derivative of sigmoid is sigmoid multiplied with minus 1 minus sigmoid. And the reason we do this is because we already calculated sigmoid there. Why don't we reuse that here? So a lot of the rule that we try to use in this back propagation is the same one that's already calculated, and try to reuse them. But anyway, the idea is that you can go backward and along the way branch it out and get the final derivative. That's how you calculate the final derivative to update the parameter. And all of this was derived from a simple idea of changing your parameter a bit to update that. I think the key takeaway here is that the loss is not just any ordinary function, it's a big function of all of your parameters. And your input, since you only work on a specific input, they are frozen. But since the input can be different, like if you look at a completely different image of a cat, it's unpredictable. You cannot see the whole loss function on its own. Those frozen values might be different on a different time and space. So that's why we have to go through all of this pain just to try to find a way of updating it. There's no way of just changing something and hope that it works. And that's it. What a good crowd. That's it. I don't want to get into further.
I have an idea. To see how much attention you guys paid.
Impromptu.
Do you guys have notebooks or anything to write on? Regardless.
Are we doing derivative?
No, we're not doing derivative. I'm going to check your guys' understanding and intuition. We did all of this for a very simple, or we did all of this for a very simple, like single neural network, right?
More complex.
So this was for x going into some neuron multiplied by the weight and a bias, and you get a y value, right? Let's add complexity, and like
I have that here.
He demonstrated that you can get the loss value based on your prediction, and then check how that changes with your weight and your bias. So now I'm going to quiz you.
Oh wait, before we go there, I'm just gonna mention something you did by yourself, right? If you use like library, again, you don't have to know all of this. You don't have to do it again and again. It's painful. Even there's library out there that you can use. It's only painful enough to do so. But the cool point is that those library allow you to compose function of your model. So you have your, let's say, linear, which is a bunch of dense layered together. you have your values, and then you compose them in this form, and at the end it gives you a model that you can use. And this model is just a function, right? After that, you can use this model to calculate loss. So this value comes in here, and you got your loss. And some library just allow you to say loss not backward, right? Hindward. Backward. Yeah. You do that, it do the back propagation for you. You don't have to know about it. It does this. It back propagates itself all the way to all of the parameters that you have. And those parameters, let's say I have W variable, and this is real. W is created as a tensor, as a number, feed it in, and you call backward. When you got back here, you say dot rat. It gives you the derivative of your loss with respect to itself. And that's how you can use this to change the stuff. So you don't have to know all of those, but the idea stay the same. Back propagation, backward, and it gives you the values. Who's that? So if now you have two inputs going into one neuron with some bias, and that goes into another neuron, and that gives you your output. How many parameters in this network? No, the total number of parameters in this network. Parameters are things we change. The things we can change. How many parameters in this network? 9. Where are they?
Am I kind of like the two inputs, the two weights, bias? Do we have bias?
We do have bias. We don't change our inputs.
Okay, so
Inputs are constants.
so 7.
Parameters are weights and biases.
Alright.
This is like for a given true sample, this is constant, and then your y value, y true is constant. The only thing you change are these two.
So for free, 2 weights, 1 bias, then another one for the second neuron. That's 4. Y is 5.
Y is not 5.
Wait, no, that is
This is just up.
okay. So 4.
The second neuron also have
Bias.
Okay, so
Right? So you have W1, the first weight for the first left, the second weight for this. I'm gonna put this in. The second weight for the first left, the bias for the first left, that's 3. The first weight for the second left, and then the bias for the second left. 1, 2, 3, 4, 5. Right? Yeah. Let's say now we talk about our loss, and we use the same loss function, but maybe squared, right? Our loss is the y value minus yt squared, right? What is y decomposed into? How can I decompose this y into the inputs for this? Let's say I'm taking just this neuron into account, right?
okay.
So the inputs coming into this neuron is, let's say, some value z. Z is coming into this neuron.
So it's Z plus W, Z plus WZ times WZ plus BZ
Yes,
minus the Y target.
exactly.
Then you decompose that back.
Yes. So this can be decomposed into W, 1, 2, like second layer, first weight of Z plus the bias of the second layer, and then minus Y2 squared. To go back again. Let's take, how does Z decompose now? Right? Because Z is the output of this one.
First layer. So that
So how can I decompose Z now?
X1 times weight 1 plus X2 times weight 2 plus bias 1
Plus too low. Too low. Easy. I'll do it over here. You said
plus
X1 times
weight 1
weight 1 for the first letter,
plus X2
Plus
times weight 2
x2 times weight 2 for
Plus
the first letter,
the first bias,
plus the first bias,
all of that times the
all
second
of that
weight.
times
The first weight of the second layer.
first weight of the second layer,
Yep.
Yeah.
And all of that plus the second bias.
all of that plus the second bias,
Yep, and all of that minus the true Y.
and then all of that minus the true y value,
Yep, and then square.
and then square. Right?
Yeah.
See how big the function gets.
And then we
The
have
same
another
loss,
layer,
as you
right?
said, was a function of, like a big function of all your previous inputs for a single one is still the same. But just like we can go backwards like this, right? So
We have Halloween.
I'm thinking of another way. So this was a backward pass. Now I'm gonna make this even more complicated.
A 1, 2, 2, 1.
I'm gonna do 3, 2, 1. Okay. So I have
I should have bought paper.
yeah.
Oh, it's
still recording.
Okay, that's great.
Actually, I'm gonna do 1, 2, 1.
This is sheet without the
Here.
one. It's down there. Okay, nice.
With let's say 3 inputs. X1, X2, X3.
Learning
Right.
a lot,
And now I'm gonna say divide this, right? And instead of taking each variable at a time, I'm gonna turn all of this into an array or a vector. So all of this will just be X. And all the weights here will just be W1. Okay? And then more complexity. I'm going to add
I need to see that.
an activation for each of these. Actually, let's call this let's call this activation to all of them. Doesn't matter what it is, just some function. So like A or whatever. Let's do the forward pass to this number. Right? So I'll help you out for the first letter, but from then on, you guys have to tell me. For the first letter, I'm taking my input, or let's say Z, the output, the linear output of the first letter is the inputs multiplied by the weights for the first letter. The only reason I'm like converting it all down into like this vector matrix is just so I don't have to write 2, 2, 1, 2, whatever. Right, so now we're just talking about the letter plus the bias for that letter. Right? That's the linear output of this. And then the activation for the first letter is just going to be the sigmoid of the like all of that, right? Z1. That is what we get out of here, at the output, this lab. Now, second lab, Z2. What is that going to be?
There's multiple Z, or
The linear output of the second lab. What is that going to be?
Can you enumerate which one is one?
Oh, yeah, sorry. This one is layer 1. So all of the weights here, W, are W1, right? And then after this operation, I get A1, right? A1 is the output of that, right? And then, now I'm talking about this layer 2. Layer 2. I want to calculate Z2. Z being the inputs coming into this layer multiplied by its weight of the bias. Right? What is Z2?
So the input is the input is A1.
The input is A1, as great. Yeah.
A1 times weight, the first weight of the. I don't know what notes.
We're just considering all the weights just for the lab.
Okay.
Right?
Plus the bias.
Sorry.
Oh.
Multiplied by W of the second, all the weights of the second lab.
Yeah. Plus the bias.
Plus the bias of the second lab.
Then that goes into an activating function.
That goes into an activation function. So A2 is now whatever the activation function is of Z2. Right?
Right.
And that goes here. So this is our third layer, our final output layer. This one. Right. So you tell me what is Z of 3.
You want to do it?
Yeah, someone else. The linear output of the last layer.
I think I misunderstood.
Yeah.
This part,
Yeah.
you have two layers.
We have 2 neurons, correct?
Yeah, but you were getting as a result only one result, which will go past to the third layer.
Wait, what?
How many inputs the third layer has?
The third layer, this one.
Yes.
It has 2 inputs.
Yeah, but we calculated one or
No, so that, okay.
we compress them into one
We
array.
compress, so
We compress them into another vector.
X is X1, X2, X3, right? That was X. And then W1 is W11, W21, W31, like this. So
It's a vector.
it's all, yeah, it's vector. So Z1, the output of this layer will be one number because I have one neuron. But it's going into 2 separate neurons.
Yeah.
So the input of this layer will be Z1.
Oh, A1 in this.
Oh, A1 multiplied by their respective weights.
So A1 is, think of A1 as just another. Think of the weight, like weight 2.
so A1
That's
only
another.
has two layers.
Yeah.
Yeah.
Okay.
Yeah,
That's why I was like,
Yeah.
where is it?
Okay, so come back to Z3. How many inputs coming in to the third neuron? How many inputs coming in? 2, right? So, and what is the input coming in?
As we just said, A1. Oh, sorry, what it was? A2. Sorry.
A2. The input of the third layer is the activated output of the first layer. So that's A2, right?
And let's do the same.
Let's do the same. So what will I multiply it with?
You want me to?
Yes, I want you to tell me.
What is it? W3
W3
plus B3.
plus B3. And this is my output Y.
Ah, yeah.
Wait, there the activation function.
Oh wait, yeah, no, activation.
This is actually
Good catch. Activation function of the third layer will be the activation on Z3. And this is my output Y. Forward pass to the network. That's what happens when you give it an input. Now, this is also, since I compressed all of these down into one number, it doesn't matter.
I was like, oh.
I mean, mathematically speaking, the size doesn't really matter as long as the shapes are compatible. What I mean by that is, if I,
You have to talk about dot product and matrix.
yeah, and in terms of like when you multiply two matrices, you have to take the dot product. There's some constraints with the dot product where the number of rows in one vector must be the same as the number of columns in the other vector.
Wait, I think I might have an idea.
Yeah.
So we have our neurons, right? So you have your neuron and it's taking a lot of input. And in practice, we don't take those individually. We compress them into a vector, which is an array of number. That means you have to compress everything else to those sort of mathematical objects. It's called tensor. That's what I was talking about the other. So input is a vector. You got your x1, x2, x3, blah blah blah, xn, and this is just big x, or maybe it's a small x for now. I don't know. How do you put your weight into a mathematical object? Well, your input is just a 1D array. Your weights can be compressed into a 2D tensor or 2D array. But there's something weird about this. The shape of your weights look like this, where you have 3 rows multiplied with the number of your input. So let's say it's n, you have 3 by n, the 2D array. And each row corresponds to a list of weight for each of these neurons. So this row contains each one of these. This row, same thing. This row, same thing. Now let's call this W. Big W, it's a matrix. That is your small x. Vector. The expression that we usually do with the linear combination is that we multiply x1 with weight x2, blah blah blah, and add them all together. So I'm just going to rewrite them. Plus x2, weight 2, blah blah blah. Same thing here, but this time is weight 2, 1 plus x2, weight 2, 2, and so on. And you can sort of see that expression everywhere. Every time you want to calculate this, you have to go through all of these. But there's a nicer way if you put them into matrix and vector. And that nicer way is simply take your weight, do something called matrix multiplication or dot product with your input. It has to be this direction. Weight, vector, or input. And the reason is because if you know matrix multiplication, it would look like this. So I have my matrix of 2 by 3, and a vector of 3. I explained this yesterday. The recording didn't go through. It's fine. But yeah, if you do it this way, the way to do matrix multiplication is very simple. You take this, you flip it. So it would look like this. Right? And you shrink it down bit by bit. So you have that, you put it on top of this, and elements that align multiply together. So it would equal to a new thing that multiplies, and then at the end you add them. And then you do the same thing for the second row. So this bunch of circle. So look like that. Take this, put it, boom, boom. And if you have noticed, it's the same thing that we want. There's a proof, but each of these weights and input is the exact same value if you organize them correctly. And you have to organize them correctly, otherwise the weight will mismatch. So metric multiplication, look like that. And in practice we do this, we don't go through number and then for loop them. Group them and do it. And another reason you do this is because it's faster on GPU, because you can distribute it, you can calculate it parallel but at the same time. So that's another thing, right?
Yeah. Okay. Now, one last quiz to check your intuition. We did all of this, right? Where for series neurons we propagated backwards. We just did the forward pass here for this model, for this architecture. Let's do the backward pass for this. So as we said, there are how many parameters in this network? Think about it while I make some space on the board. How many parameters in that network?
30 seconds to answer the question. I'm listening in the back.
Yeah.
Just look at the network. See if you get it wrong. 3. Are you including the biases as well?
Yes.
Okay. Sorry, oops, I should have said anything. Go ahead.
Hmm?
It's a trick question.
Okay. Each person give me a guess. You said what, 16, you said 11? 11? Are we on a consensus or just a calculation? First layer. Every input has one weight corresponding to that.
Yeah.
Right? So 3 weights plus 1 bias. That's 4 so far. Next layer. 2 lines going up. 1 input to every neuron, 2 weights. 1 bias for every neuron. So second layer we have 1, 2, 3, 4 weights. That's 4 plus 4, 8. 9, 10, 11. 11. We said that using backprop we can get the amount that we need to change each parameter with, right? Using backpropagation. And we have 11 parameters. Let's do that for every single parameter.
Oh boy.
Oh, right.
Going backwards from here.
That's why you melt CPUs.
That's why you melt CPUs.
That's why you spend hundreds of billions of dollars, and that's why you spend.
Yeah, for reference, how many parameters in ChatGPT? Like 700 billion?
And that's
Yes.
why NVIDIA sell their AI
Yeah.
for a couple 100,000.
Yeah.
Because it's expensive.
Let's see how long it takes us to do it for 11. So, going backward, or I'll just say loss again, is the y minus yt. And we don't have to get this formula. The only thing that we're going to do is write it symbolically, as you said. dl.
One thing though
Why?
if you compress them into vector and matrix, you could just use that and take the derivative on that operation instead. So instead of operation on smaller thing, it's an operation on bigger metric multiplication. But the derivative of metric multiplication is very weird if you want to figure it out. Yeah, you don't have to like go through each number anymore. So if you compress them on this high level ideas, derivative on it instead.
So,
Can you evaluate a limit of matrix?
you do
Yeah,
it for every
that's what
single
it's
element.
It's called
Yeah.
Jacobian matrix.
dl with respect to dy. What is y dependent on?
More dependent on
The activation of Z3.
Yeah.
So this would be d of
Okay, just a separate thing.
yeah.
There's a small group meaning like everybody here, plus a few others. I was supposed to do the math, the discrete math, right? Remember we started that and stuff, like you just did a week or whatever. This summer maybe, the club, or currently always running, the club should probably do what the college is not doing in the fundamentals of math. Not going through everything. You take people just from the basics, exercises. It doesn't take long. It might seem hard if you're not familiar with it. You know, you did it in high school. You did it in high school trying to remember. So the things like up to the chain rule and partial differentiation is pretty simple. Basically, it's just differentiation. They keep one thing constant. It's just like it's really simple. I think rigor in that might be useful. So maybe that's something you guys could ask the club to do or have running all this, a small group. Not many people will be in it, but it will make you allow you to run instead of crawling at least, right? Because the mental capacity is more than there, right? And therefore, these will become trivial. I'll just bring that to the club, and you guys to pressure the club that you ought to probably have a small little set of sessions on that. See that I was not able to do that this semester. I'll go back to quiet again.
Things we want to change, parameters. Let's take parameters in the last lab specifically. We want to get how the loss changes with respect to parameters in this lab, W3. So, what is the loss directly dependent on? The predicted value, right? So, Y is just activation on the third lab, right? So, we can say loss is directly dependent on the activation on the third lab, right? Going backwards. What is the activation directly dependent on?
On Z3.
Z3. The activation on the last lab with respect to Z3, right? What is Z3 dependent on?
Weight free.
Weight free
and bias free.
Right? So now we've gotten to weight 3. If we're trying to compute the derivative of the loss with respect to weight 3, we can get the derivative of Z3 with respect to weight 3. And that's it for the parameters in this lab. Let's move one layer backwards.
What about bias?
Hmm?
What about bias of that?
And it's the same thing. You just replace W with B.
Yeah.
Because they're both dependent on the same thing. Let's just do weights for now.
Okay.
You can mess around. Let's move one layer backwards. B of L respect to weights in the second layer. So, what is L directly dependent on?
Do we get to skip or do we
No,
have to,
not for this layer. Maybe for the first layer we'll skip. But what is L directly dependent on?
Going back again, it's Y.
Y, which is
Z3.
A3,
Yeah.
right? So, D of A3. What is A3 directly dependent on?
Z3.
A3 is directly dependent on Z3. What is Z3 directly dependent on? What is Z3 directly dependent on that will let us move back? So if we stop at weight here,
Oh, yeah.
A2. Perfect. What is A2 directly dependent on? Z2. And then what is Z2? Now we have Z2 all the way here, which is directly dependent on our weight, so we can just take the derivative all the way back. The Z2 with respect to the W2. Back prop. Make it even longer for the first time. But we computed this already, right? For the first time, that's what you're saying, like we can skip it. Because as we're propagating backwards, we will begin to compute most of these. The only place where we differ is here onwards. When we do it for the first layer, most of this will be similar. Because the only thing we're changing is technically this one. Right? Because we're not taking the derivative with respect to the weight, we'll be taking the derivative with respect to the activation of the previous layer. That's how it all works. It's just one big function. Forward pass and backward pass. That's it. Now you mess around with different architectures of this depending on the number of inputs you have, the amount of relationships you want to compute, the amount of outputs you have, or like the amount of outputs your problem needs. And you do the same thing. That's all for like dense neural networks. Apart from that, depending on how deep you want to go. From here, you can go down into like a lot of different branches. I think in the summer, we might do CNN, probably. Which is, again, the process is still the same. We just change the architecture.
Yeah.
But if you want to go down not the image processing route, there's a lot of different places you can go. That's it. Mess around with this. Check your understanding. What's the time?
Oh, a lot.
11:30.